This is the first video of this playlist. We're going to start with introducing the concept of using block matrix. And we're going to give a short description about how you generalize linear function, quadratic function in terms of vectors. And after that, we're going to see that quadratic function of vectors involve a symmetric matrices, and we're going to talk a little bit about important properties of symmetric matrices. So let's start with a matrix that we know. Suppose you have a matrix A like this, but now a lot of time we're going to look at this matrix A into blocks, into sub blocks. So you can partition A into this, into that, okay? But one of the block pattern is that you consider leading block. So the leading one block that has size 1 is the number 0, okay? The second leading block is gonna have 2 by 2 size is this matrix. The next leading block that's going to have dimension 3 by 3 is going to be this. All right. So you're looking at the leading n by n block basically. And now you're going to have 4 leading blocks, and the last one is actually the matrix A itself. Okay. Once we determine the leading blocks, we can talk about the leading determinants. All the leading blocks are square matrices. So the leading block, the first one, the determinant is 0. The second leading block, 0 minus 0, the determinant is 0. And the third leading block determinant is, you can calculate it, is negative 6, and so on, the last one. When you compute all the leading determinants, these are called principal minors. So you have first principal minor, second one, third one, and the fourth one. You have n principal minors for a square matrices, matrix. Now, next, I'm going to talk about linear function and quadratic function of vectors. Suppose you have a constant vector w and you have a vector x. The concept of a linear function ax plus b for the scalar case now is extended to a linear function of a vector of n variables into R. A linear function is described by some constant vector doing inner product with x. So it's w1 x1 plus w2 x2 and so on. Okay. It can be shown quickly that it has the linear property because alpha of f of alpha x plus y is going to be w transpose alpha x plus y, and that is equal to alpha w transpose x plus w transpose y. So it is actually alpha fx plus fy. So the superposition holds, and this is linear function in Rn. Okay. When a linear function is added with a non-zero constant, it is called an affine function. And that B is we call it a translation term. In the scalar case, you can check quickly that the derivative of y with respect to x is simply a. Okay. For a linear function of a vector form, you can talk about the concept of a gradient. The gradient of f at x is going to be a vector where you just use the partial derivative. This is del f by x1, del f by xn, dot, dot, dot. And you can see from linear function is that the gradient is given by w1, w2, dot, 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 wn. So it's actually the coefficient w here plays a role of the gradient vector. The ith component of the gradient gives you the rate of change of your function f in the xi direction. So you can say if your gradient is 0, negative 1, 0, 1, what you can say is that in the direction of x1, the rate of change is highest, all right? and there is no change in your function f, even though your x3 is changed. Okay. And linear function, what else can we use, or what else, where else we can see the usage of this linear function? How about the set, a set of x where your linear or affine function equals to a constant? This is called a level set or a contour of the linear function. It turns out to be a hyperplane in Rn, right? Suppose this is W transpose X plus B. This is a hyperplane in Rn where the gradient W must be perpendicular to your level set or the contour. So when W is pointing, suppose W is pointing to that direction, it means that whenever B decrease, your contour is moving this way. It's moving to the other side of your gradient, because the gradient vector is the direction where your f increases, right? That direction. Um, you're gonna see a lot of linear function in linear regression model or the linear classifier models. Okay. So now let's talk about quadratic function. Okay. In scalar case, you can have functions like x squared minus 3x minus 5, things like this. Okay. And now, if you have n terms, if you have a function of a vector x, x1, x2, x3, for example, and this function maps to R, and now your function is mapped in a quadratic sense, general definition of quadratic function in Rn would be x transpose Ax. So you can see here is a quadratic function in X, and what it does is that actually uh, computing all the possible products of xi and xj with the coefficient aij. I hope it's not that hard. Maybe you can try with 1 to negative 5, 1, 1, 0, 0, negative 1, negative 2, negative 3, for example. Just multiply x transpose, which would be a row vector, and a matrix A, which is square, and a vector x. The dimension would go to 1 by n by n, and n by 1. So these function map from a vector to a scalar. And please verify yourself that when you do the computation, the formula of x transpose Ax is this way. For example, with this A at the end, if you just calculate it yourself, x transpose Ax would be 1 times x1 square plus 2 times x2 square. The term in the diagonal would be the square of xj plus 5 times x3 square. And what about the cross term? So it's going to be 1 times x1 x2, 1 times x1 x2, and plus 1 times x2 x1 plus 2 0 here, 0 times x1 x3 plus 0 times x3 x1. Last one would be the pair of x2 and x3. You would get negative 2 x2 x3 and 3 here plus 3 times x3 x2. Okay, this is how you expand the quadratic product. What we can see is that now I would like you to take a look at this guy is 1 by 1, right? So if we transpose of a scalar 1 by 1, you should give, by the transpose operation, it's going to be x transpose A transpose X. When you have 3 terms in multiplication transpose, you have to transpose the last term first, and transpose of A and transpose of X transpose. So you get this one. But because you know that this one is a scalar, after you transpose it, it should be equal to itself, right? Like you transpose 2, you get 2. So this is why you can also you can just split your X transpose AX because it's equal to this by using A transpose. So you can split that is equal to X transpose AX half plus X transpose A transpose X half. What it shows here is that whatever A that you use, which is square, right? Whatever A you use is when you consider the quadratic function in X, where we call the energy form here. When you consider the energy form of X with coefficient A, it's going to be the same as using plus A transpose half. And if you notice that you can always decompose A into this guy plus this guy, always. However, this guy has a very meaningful interpretation because this guy, if I make a scratch here, is always symmetric, right? It's equal to itself, where this guy is skew symmetric because A minus A transpose half transpose, you get A transpose minus A half. Skew symmetric means when you transpose of that thing, it equals to the negative of that thing. Okay. In short, any square matrices can be decomposed as a symmetric part and skew symmetric part. And what it says here is that the energy form of X using A is always equal to the energy form of X using the symmetric part of A. So from now on, we can assume that whenever you have the energy form involved the X, you just take the symmetric part, or you can just assume that A is symmetric. Because if A was not symmetric, what you would do is just take the symmetric part, A plus A transpose half. Okay. So from this slide, I want you to get used to this expression. Given A, can you expand this? And on the other hand, if I give you the quadratic function in X, where it's expressed as, the quadratic function of each component, can you go back to the matrix form? Okay. Maybe you pause the video and maybe determine what A is. And after you scratch it, what you can see is that now you can read that, of course, the coefficient of xk squared is going to be along the diagonal. All right. And because negative 1/2, negative 1 is going to be the 1, 2 entry, it's going to be here, But because this is negative 1, you're going to split 1/2 and 1/2 here. Because you're going to multiply between x1 and x2 twice. So this coefficient is going to multiply with x1 and x2 one time. And for another time, is here. Negative 1/2 is going to multiply with x2 and x1. So that's why you read this coefficient and split into half. From this coefficient, it's going to be 2, 3. So that's the this position. So it's plus 2. So you split it into 1, 1. And there is no cross term between x1 and x3. So that's why the 1, 3 elements of A is 0. And this is how you convert it. Please, maybe it's a good exercise that a lot of time we have the energy form, and later on we're gonna check some condition about your energy form, whether it's always non-negative or not. So in that sense, once we have that question, it's always nice to get you get practice on completing the square. For example, you have a quadratic function in x1 and x2. Okay. Now what I'm going to do is that I'm going to complete the square. I look through the coefficient 14 here, so I divide it into divide it by 2. So I complete this term first, and I see that I'm going to have 49x2 squared after expanding the square. So I compensate this term in order to match with the original expression. Okay. So this is how to complete the square. So on this slide, how about computing, expanding the energy form and complete the square? Please pause the video and do it, and now we can check the answer. The first one is x transpose ax it would be 4x1 squared plus 13x2 squared plus 2 times 6, which is 12x1 x2. For B, it's going to be 4x1 squared plus 9x2 squared plus 2 times 6 is 12x1 x2. For C, it's going to be 4x1 squared minus 4x2 squared plus 12x1 and x2. Okay. I hope that you get exercise on how to complete the square here. For example, um, so it's 2x1, right, plus um 3x2 squared. All right, first you complete the square. You look at this one and this one. And of course, 2x1 would match with this term, right? 2x1 times 3x2 with a factor of 2, that gives you 12x1, x2. And now let's check about how to make it equal. This is going to give you 9. From this, it's going to give you 9x2 squared. But originally, you have 13. So you must add 4x2 squared. Okay. And of course, when you see this, it's going to be this. And when you complete the square of the last term, what do you get? You would get, I mean, from this one, you have 9, right? But you want negative 4 here. So you subtract by 9, subtract 13, x2 squared. You get minus 4. Okay. We're gonna come back to where we can exploit or we can play with the energy form and its completing square again. But so please keep these exercise in mind. Next, when we're ready, when we get familiar with the energy form, now we can talk about quadratic function. Uh, in scalar, y equal 3x squared minus 7x. This is an example of your quadratic function in a scalar variable x in vector form. Okay, our quadratic functions involve first the energy form in x though, or the quadratic function in x using the coefficient p, but it also could have the linear term and the constant term. So this is like generalization to this term. Linear function is generalization of this term and the constant value. Okay. Um, this term is also known as the energy form because what we see in physics and real life application, it would be that quadratic function, a lot of time it represents the power or the energy. Okay, electrical power of that is absorbed in a resistor R, where there's a current is I. We know that is I square R, so it's quadratic function in I. Kinetic function, where there is a mass m moving, there is a particle with mass m moving with a velocity v. The kinetic energy is a quadratic function in v. Or it is the potential energy stored in a spring that is stretched with the distance x, right? So it's kx squared, and that is the quadratic function in the distance x. So we have seen this quadratic function or the energy form all the times in real life. When we analyze the quadratic function, we also look at the contour shape or the level set. What we mean is that what is the state of x that my function is is a constant. This this thing is called a level. As you vary the level alpha here, you get different contour. All right. I make a short note here is that the contour shape of f depends on the property of this p. It involve the property that we call positive, definite, indefinite, and so on. We're gonna learn it in the few videos after this. Okay. Let me just plot that. Okay, first of all, is I assume a matrix P and all of my eigenvalues of P are positive. So the plot of this quadratic function in R3 is going to be ellipsoid, like a rugby ball, and in R2, so this is the ellipsoid in R2, kind of oval shape. Okay. Let me make a short definition first, like, but we're gonna come back to this, okay? When all the eigenvalues of symmetric matrix P are positive, that P has a property that is called positive definite. And when you use this P to describe the quadratic function, it's going to have the ellipsoid shape. We can characterize the ellipsoid by looking at its principal axis, right? The direction of this axis and the width of this axis. It's going to be we have video after this. It's going to relate it to eigenvalues, eigenvectors of P. Okay. Now some example of my P. I have I have P equals to this matrix, all right? And if I calculate all the eigenvalues of P, they are all, so they're going to have two eigenvalues in this case. All eigenvalues are positive. When I plot the surface, because my variable is x1 and x2, okay? So when I enumerate all points in the grid of x1 and x2, and I use this peak, I calculate this function. The function value is going to be on the vertical axis. It looks like a bowl. You have upward shape, and if I plot a contour, it's going to be ellipsoid. Okay. When my p is 1, 1, in this case, my lambda p, that's going to be non-negative, or one, like at least one of the eigenvalue could be 0. There is one term. Um, what I see here is that the surface or the function value seems to be that in some direction of x, my f increasing unboundedly, all right? And there could be some direction of my x that my f, my function value, could go to negative infinity. So when I plot the contour, so you can see that some of them may have oval shape, and then you're gonna have that something look like a slab, and the function value is unbounded. Um, if I plot the third case is when my p is 2, 1, 1, negative 1. In this case, eigenvalues of p contains a mix of positive and negative sign. So what I end up with is that the surface of my P has two possibilities. In some direction of my X, when my X toward that way, my F grows infinitely, right? When my F kind of go to this direction, my F decreases to negative infinity. So when I plot a contour, it looks like hyperbola shape like this. Okay. So as the quadratic function, as we see previously, the quadratic function in P is always equal to the positive part of the matrix P. So, and that's what we said. You can assume later on, you can assume that P is symmetric. So here, I would like to talk about some important property of symmetric matrices. We say that A is symmetric if A equals A transpose or Aij equals Aji. Okay. Example in block representation, if my A has sub-blocks like this, okay, it basically means that my 1, 2 block and 2, 1 block has to be the transpose of each other. Uh, let me remind that when you transpose the block matrix, suppose A, B, C, D, if you transpose these things, you can work, you can take a look at this as a transpose of 2 by 2, but you do have to transpose of all the subblocks inside. For example, this is going to be A transpose, B transpose, C transpose, D transpose. All right. So in order for a block matrix, this guy to be symmetric, this pair has to be the transpose of each other. Mm. We see this in application as well. For example, correlation matrix or covariance matrix. Okay. Suppose A is rectangular. It doesn't have to be square. You can verify quickly that this guy and these guys are always symmetric. A transpose, if you transpose it again, remember um, when you have B C transpose, that is C transpose B transpose. So A transpose is going to be A transpose times A transpose, and that is A transpose. All right. So this guy is always symmetric. A transpose A is always symmetric. Let me test your understanding. If my A is P by N, all right, rectangular, what is the size of A transpose, A transpose A? You pause the video and answer this question. A transpose is going to be P by N, N by P, and that turns out to be P by P. For A transpose A, it's going to be N by P, P by N, turns out to be N by N. Okay. If A is symmetric and invertible, and that's implicitly assume that my A is square. Otherwise, you cannot talk about like being invertible. Then, if that assumption holds, A inverse is symmetric. All right. If you take the inverse and then transpose, it's going to be the same as A inverse. Okay. The third bullet is that if A is invertible, A transpose and A transpose A are also invertible. This can be proved quickly, or I hope you prove, okay? And the inverse is going to be, I hope that you prove that the inverse of this is going to be A inverse and then transpose times A inverse, all right? And A transpose A inverse is going to be A inverse transpose. Okay, please verify yourself. Not that hard. Let's talk about the crucial results here. Actually, it turns out that the symmetric matrices has a nice property. First, all eigenvalues are real. Mhm. Let me point out that when A is square, eigenvalues of A doesn't have to be real all the time. In this example, characteristic equation is this, right? And your eigenvalues are, both pure imaginary. All right. But we have this nice result that all eigenvalues of A are real. Okay. Secondly, eigenvectors are orthogonal. Okay. Orthogonal means that suppose you have U1 and U2 that are eigenvector according to this. Orthogonal means U1 transpose U2 equals 0. Okay. We're gonna prove the bullet 1 and 2 in detail, but let me just point out the results of that. Okay. Suppose your A has n eigenvalues, all right? N eigenvalue, and you have n eigenvectors. And suppose you stack your eigenvector into a matrix. Okay. So when you multiply with A, that's going to be AU1, AU2, dot, 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 AUN. All right. And because these UK are eigenvectors, you have this. And that is like you scale each eigenvectors with lambda k. And when you scale the all of the column vector in this way, it's the same as you multiply the diagonal of lambda on the right hand side. Okay. So if I call this guy a matrix U, and I call this guy a matrix D. Okay, my matrix D contains the eigenvalue and it has a diagonal property. Everyone should know from this linear algebra that eigenvalue decomposition of any A admits AU equals UD, or that A equals UDU inverse for any A. This is for any A that can be diagonalizable. However, when A is symmetric, we have the property that we're going to prove later that UI transpose UJ is 0. All right. So how about hmm, if I if I calculate U transpose U with the assumption that my U is eigenvector from symmetric matrices, okay, now you have to transpose correctly. If my U is this matrix, now I'm going to transpose it. So it becomes U1 transpose, U2 transpose, dot, 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 UN transpose, and multiply with U, which is U1, U2, and UN. And if I expand this, what I'm going to get is that U1 transpose U1, U1 transpose U2, dot, 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 U1 transpose UN, dot, 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 UN transpose U1, U2 transpose U2, dot, 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 UN transpose UN. Let's check the dimension again. If you could get confused, this is what n by n, this is n by n. What you see here is actually like I partition. I mean, this is like one row, second row, and nth row. This is like one column, second column, and the nth column, right? And of course, the result must be n by n. But as you see that each term is actually the inner product between ui and uj. Now let's talk a little bit about eigenvector. As you know that your eigenvector UK, for example, if it's 1, minus 1, and 2, remember this fact that you can normalize your eigenvector anywhere you like, and it's still an eigenvector. So I can normalize by its magnitude. For example, I can normalize by 1 square minus 1 square plus 2 square. If I normalize it this way, my result is that the magnitude of my utility is going to be 1 always, right? So I'm going to normalize. So basically what I mean is that you can normalize your eigenvectors in a way that your ui transpose ui, which is going to be um, ui1 entry square dot 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 uin entry square is all equal to 1. In that sense, when you do that, the diagonal here is 1. Okay. And now I'm going to use the second fact that all eigenvectors of A are mutually orthogonal. So it means that ui transpose uj is 0. What I have is then all the off diagonal term is zero. Okay. Then what happened? What we show is U transpose U equals identity matrix. For symmetric matrices is nice. When U transpose U equal identity, you just found out that actually the inverse of U is U transpose. Because if you multiply something with a matrix and it gives you identity, that thing is your inverse. In this case, your eigenvector matrix is nice. The inverse is not hard at all. It's just the transpose. When we plug this into the original form of eigenvalue decomposition, that's why we have this nice property that for symmetric matrices, the eigenvalue decomposition, instead of having U du inverse, but it becomes U du transpose. Okay, and what we're gonna use all the time, the eigenvalue decomposition of symmetric matrices. For example, I'm going to derive these useful inequalities by exploiting this decomposition. I can show that whatever energy form of A, you can always derive upper bound and lower bound like this. Any quadratic function of x, whatever values of x, it can be bounded above by lambda max of A times the magnitude of x. So by this notation for now, I would like you to take a look at this, that we're going to introduce the concept of norm later in the next videos, but right now you can think of the magnitude or the size of the vector. So it is the component of x1 squared dot 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 component of xn squared. And you should know that this notation is the same as x transpose x. Okay, now let's prove it. X transpose AX, if you use the eigenvalue decomposition for symmetric matrices, okay. So now you can call this guy Y. U transpose is gonna be n by 1. U transpose is gonna be n by n. X is n by 1. So this is your vector Y. And this is your Y transpose. And C, this is going to be y1, y2, dot, 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 yn. And what is your D? Your D is a diagonal matrix that contains eigenvalue in A. Okay. And then when you work with energy form with coefficient that is a diagonal matrix is simple because it becomes lambda 1, y1 square, lambda 2, y2 square, dot, 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 lambda n, yn square. It's simple. Now let's talk about y1 square, dot, 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 y2 square. Okay. Now we're gonna exploit the property of the U matrix U that has a nice property that U transpose U equals I, right? We're gonna assign its name later that we call it unitary or diagonal. Okay. So let's talk about the norm of Y, which is Y transpose Y, right? But my Y is U transpose X. You do the transpose, that's going to be X transpose U, U transpose X, all right? And because U transpose U equal U, U transpose equals I, and that is simply X transpose X, or the norm square of X. Okay, this is one thing. This is one note. It turns out that whenever y is a linear combination of x in by using the matrix U that is unitary, the norm of U doesn't change. I put one note here. Suppose your x is here, right? For other matrix, for example, mx, when you multiply a matrix with a vector, the direction can change, the magnitude can change. What we have derived here is that when you multiply X with unitary matrix U or U transpose, the norm of Y doesn't change. It is the same as X. So what it means is that your matrix, your vector U transpose X is around here because the norm has to be the same as X. Okay, that is one result. We put it aside. Let's continue on this quantity. What can you say? Now we have derived for any x, any energy function in x is quadratic in y in this way. Okay. Now, if I want to make a bound, if I want to find an upper bound of this, is it true that I can make the lambda max of a as a common factor, and then I multiply with this? Do you think it's do you agree with this bound? I mean, all lambda 1, lambda 2, and lambda n, right? For example, you have 2y1 square plus 5y2 square negative 3y3 square. You can just pick the maximum one and make it a common factor, right? And that's it. That's how we proved an double bound. This is the same as the norm of x squared. Okay. So that's why we have this upper bound that energy form in X using the matrix A is bounded above like this. The lower bound is not hard to show. Just pick the common factor as the minimum eigenvalues of A. Okay. So the result in this slide is important. We're gonna come back to this over and over again. But to conclude this video, I would like to spend maybe another 5 minutes on proving the number one and number two because these two properties provide many useful applications. So it's nice just to look at the proof. First we have to prove that eigenvalues of A are real. Let me recall again that eigenvalues of any square matrix can be complex. So when as I give an example, all right, something like this. So eigenvalue can be complex. So a characteristic function is going to be this, right? So your eigenvalue is 1 plus and minus 2j. When eigenvalues are complex, your eigenvectors are complex as well. So first, let's prove that when asymmetric eigenvalues are real. In order for that, so we put it in a general setting that y and x, lambda and x could be complex. And when your eigenvector x could be complex, let me use the notation x star, that is the x transpose uh, of the complex conjugate. For example, if my x is 1 minus 2i and this is my negative 5i, my x star would be a row matrix where this is 1 plus 2i and this is 5i. So this is called complex conjugate transpose or Hermitian operation. Okay, so the proof is the following. It's just similar to the energy form in X, but now I replace the transpose with the Hermitian conjugate. Okay. So it goes like this. This is supposed to be n by 1 by n by n, and this is n by 1. So the result of this is 1 by 1. Okay. So what I do is I take the energy form of x, which is complex number now, and I take the complex conjugate of a scalar value. But I mean, I leave this vector form, and what I do is that I just distribute this star operation to all of this. All right. So what I'm gonna do is that I'm gonna take star of this times star of a times x star x star. So that's x. Okay. Then after that, I make use that my A is symmetric. and my A is real. So when my A is real, A star and A are the same. Okay. And because my X is eigenvector of AX equals lambda X. Okay. Lambda is just scalar. I put it aside. I put it in the front. So my X star X, what is it? My X star X, what the notation say is that it's just absolute value, the modulus in the complex sense, the modulus of x1 to the dot, the modulus of xn. Okay, so it gives you similar concept of a norm. Okay, now I put that term on hold now, but I'm gonna derive by using another direction. Now I start with this term, all right, and I look at this term directly. My x star ax, my ax is lambda x because x is the eigenvector, okay? And then I make a star after that. So what I'm gonna get is x star, lambda star, and x, right? But my lambda is just a scalar. Lambda star is simply the complex conjugate of lambda, x star x. I have derived the energy form of x in two ways, the yellow way and the green way. And of course, they must be equal. And because when you match this guy, what do you get? So you get lambda minus lambda complex conjugate times x star x equals 0. All right? This term is never 0 because that is the sum of modulus of your entries in eigenvector. This is bigger than 0. Your eigenvector is never 0, so x star x is never 0. This is 0, then it means that your lambda equals lambda bar. All right, that means your lambda has no imaginary part, that your lambda has to be real. And that is the end of the proof why the symmetric matrices have real eigenvalue. Second of all, the eigenvectors that correspond to distinct eigenvalues are orthogonal. So I'm going to start with lambda 1 and lambda 2. These are distinct. Now I can assume that my lambda and my x are real because I already proved the first one. Okay. What I'm going to show is to perform the quadratic product, but using the cross term. So in this notation, my x1 is just the first eigenvector. It doesn't mean that this is the first entry of my x, okay? My x1 is a vector, my x2 is a vector. So when I do the quadratic function like this is still 1 by 1 because this is 1 by n by n, and this is n by 1. Okay, let's see. So I'm going to start with this. And because ax1 is lambda 1 x1, and because my lambda 1 is just a scalar, I put it outside. Now, this is one way. This is one way of the derivation. Now I use another way, okay? Because this is just a scalar transpose equal to a scalar. So what I can do is that I transpose first is x1 transpose A transpose x2. But because my A is symmetric, A transpose equal A. Then my AX2 equals lambda 2 x2. All right. Lambda 2 x2, I put it aside. So it's lambda 2 x1 and x2. When I derive it using this way, and both of them have to be the same, right? So I match this guy. So when you match this guy, you have this condition, lambda 1 minus lambda 2, inner product between x2 and x1 equals 0. Because I assume that the lambda j and lambda k are distinct, so this guy is never 0. So inner product between x1 and x2 has to be 0 instead. And that is a proof why the eigenvectors corresponding to distinct eigenvalues are mutually orthogonal. Okay. That is, I think this is all the properties of symmetric matrices that you should know. So third, three bullets here. And we're going to use it when we introduce the next concept, positive semi-definite matrix, in the next video.